All right. So when it comes to graphing rational functions, there is like a list of things that I want us to be able to identify. All right. And so I'm going to list those things out. Here are the kind of key parts that I want us to be able to kind of like go through. Okay. So we'll say key parts of a rational function. Remember, a rational function, like a rational number is, a number that can be written in the form a over b, where a and b are both integers. A rational function is a function that can be written in the form, I guess, like f of x over h of x, maybe, where f and h are both like polynomials or something like that. Okay? Or both functions, I guess, really. But anyway. Okay, so 1, you should be able to identify the domain of your rational function. Now this harkens back to like one of the very early lessons that we did in this class, and maybe other classes too. All right, when we want to determine the domain of a function, what do we look for? Yeah, Parker?
Square roots and second denominator.
Okay, right. So we don't want to divide by 0. You want to look for? Bless you. Or square roots of negatives, or even-powered roots of negatives too, right? Okay, we keep it real. No imaginary numbers. I'll zoom in a little bit on that too. There we go. Okay. We want to identify any vertical asymptotes. Okay. Vertical asymptotes occur, well, does anyone remember? Or does anyone know when a vertical asymptote occurs? How do we indicate a vertical asymptote? Yes?
When there's a 0 in the denominator.
0 in the denominator, but not also in the numerator. Yes, exactly right. Okay. So, I'll write that here. Yeah. These occur at x values, okay, where we divide by 0, except when we get 0 over 0. Okay? So in other words, vertical asymptotes occur when we are, what do we call it when we have a number over 0? Undefined. So vertical asymptotes occur when we are undefined, okay? And something else occurs when we have 0 over 0, which is indeterminate, right? Something else is going to occur. And that is, number 3, holes. We also want to be able to identify holes in our graph. Okay? And these occur at x values, okay, where f of x is undefined. Or not undefined, sorry, indeterminate. Okay, where a function is indeterminate. 0 over 0. I guess I'll write that here too. Okay. Holes. Alright. So those two, vertical asymptotes and holes, represent discontinuities. Right? Discontinuities. It creates like jumps or gaps or holes kind of thing. So those are two kind of discontinuities. Two main ones we're going to keep an eye out for. Discontinuities. I didn't have enough space. And I missed the C. Oh, man. All right. I'll put it here. Discontinuities. There we go. Okay. Yep. All right. All right, what other things do we need to identify? Well, the zeros, right? That's something that we carried over from when we graphed polynomials. Shh. Okay, it's enough now. Number 5, horizontal or slant asymptotes as well, if they exist. We'll talk about slant asymptotes tomorrow, okay? So you don't have to worry about those right now. I'm sure you guys did those in algebra too? Yeah, so no, some of you did, some of you didn't. Okay, well, we'll talk about slant asymptotes tomorrow. Today we'll just worry about horizontal asymptotes. Horizontal asymptotes, how do we determine those? What makes a horizontal asymptote? It's a little bit different than the idea of a vertical asymptote. So for example, a vertical asymptote, will your function ever cross a vertical asymptote? No. Can a function cross a horizontal asymptote? The answer is yes. Yes, it can happen. Now, does it always happen? No, not always. Okay. So a horizontal asymptote, that is what your function approaches as you go really, really far towards positive infinity, as x goes to positive infinity, or as x goes to negative infinity. Or in other words, the horizontal asymptote right here, we can also consider that to be what? The end behavior, right? We call it the end behavior, okay? So to find these things, you take the limit, well, actually, I guess I'll do the horizontal asymptote. To find a horizontal asymptote, it's the limit as x approaches infinity of your function and the limit as x approaches negative infinity too, okay? As we kind of like talked about before, right? I think Megan asked about this before, right? When x approaches infinity versus x approaching negative infinity, most of the time, I think Julie asked about it too, but most of the time, they're going to be the same. They'll approach the same thing. But every once in a while, we do have situations where you could have two horizontal asymptotes, where one side of your function will approach one number, one side of your function will approach another number. So, and we'll see some of those, before we go. And then finally, just additional points if necessary. This is just for your sake. If you're like not really sure how the graph's supposed to look, just pick some more points and plug them into the function to get the matching y values, and then go from there. And then finally, number 7, we graph. Okay, so 7 easy steps. Okay, we're going to focus today on what I would consider some simpler rational functions, getting the sketches down and stuff like that. And then tomorrow we'll do some more complex-looking ones. Okay. So we'll do one together, and then maybe I'll have you guys try one on your own. And that'll be it. We're just going to do 2, okay? Just 2. But you can see there's enough here for 2, right? There's enough. All right. First example. So we're going to graph, and here's our rational function. 3x over x minus 1. Okay. 3x over x minus 1. So, and you don't have to go in through the same order that I did, but I'm going to use my order because that's what I've got here, so I'm just going to do that, okay? I think I wrote the order of these characteristics in a helpful way, so it might be helpful to go through these things, okay, in the order that I gave, but you don't have to necessarily. Okay, so the domain here. Are we going to have any domain restrictions? Yes, okay. Where? At what x values? At 1. Why at 1? It would make our denominator equal to 0, right? So we can take our denominator, that x minus 1, we'll set it equal to 0, and we'll say, aha, when x is 1, our denominator is going to be 0. So therefore, our domain is going to go from negative infinity to what? 1, and then union 1 to infinity. Okay, so there's our domain. Now, part of the reason why we find that domain is because the vertical asymptotes and the holes, we're going to be able to pull the domain restrictions, and from those, we're going to kind of classify them as potentially vertical asymptotes or holes. So it's helpful to do this domain restriction concept first, to then go to, for example, number 2, where we describe the vertical asymptotes, and if you'll be okay, I'll just put VA there, right, rather than writing out vertical asymptote. Okay. Do we have any vertical asymptotes here? Yes. Okay, where? At x equals 1. Because didn't we just say that at 1, we're going to have 3 over 0, which is undefined, right? We get f of 1 equals 3 over 0, undefined, right? Undefined indicates a vertical asymptote. Our function approaches infinity, or our function approaches negative infinity. Okay, that indicates that vertical asymptote, right? All right. So that's good to know. Number 3, are we going to have any holes? Yeah, no, right? I mean, we only had one domain restriction, and it was at 1. And we already classified that as being a vertical asymptote. Can something have both a vertical asymptote and a hole in the same x location? No, it wouldn't make any sense, because you can't be both indeterminate, 0 over 0, and undefined, a number over 0, right? So it's going to be one or the other. It can't be both. since we already classified our one domain restriction as a vertical asymptote, there will be no holes. Okay, none. Right. Do we have any zeros? Do we have any zeros? Will this function ever equal 0? I'll put this, maybe I'll pose it this way, right? 3x over x minus 1, will that ever equal 0? Yes? Okay. How or when? When x is 0, okay? So this is a little bit funky now. You're like, wait a minute, how am I supposed to know when this like weird looking thing is going to equal 0? Well, don't think this is crazier than it needs to be. This is really just like a fraction, right? When does a fraction equal 0? When what part of the fraction is 0? The numerator, the top, right? So all we need to worry about here, we can ignore this x minus 1 piece, and let's just say 3x equals 0. When does 3x equal 0? When x is 0. Okay, so we have a 0 at 0. Okay, we have a 0 at 0. Okay. Number 5. Okay, we're going to now find the horizontal asymptotes. And to find the horizontal asymptotes of a function, we do what? And behavior, so we'll take the limit as x approaches positive infinity of 3x over x minus 1. Just like we did in the warm-up. Degree of the top is 1. Degree of the bottom is 1. They're the same, so what's our answer going to be here? 3. Okay, let's try negative infinity just because, for completion's sake. It's not really necessary though, but let's just imagine it here. Well, we're going to have 3 times negative infinity over negative infinity. So it's a negative over a negative. It's going to become positive again. So it's going to be 3 as well. Okay, so it's not necessary to check here. They're going to end up both being positive 3. So yeah, what's the equation for a horizontal line? If we know that the horizontal asymptote occurs at 3, what would the equation for that line be? Y equals 3. Yes. Horizontal line, right? Horizontal lines are y equals a number, so y equals 3 would be our equation there. All right. And before I go into any additional points, I guess I'll like leave space for that. I'm going to go to the graph and see if I need any more points than that. Okay? So I'm going to go ahead and go over here and graph it. And we'll see if I need more points. Okay, so I'm going to try and take all this in here. I see that I need x equal to 0 to show up. I need x equal to 1 to show up. I need y equals 3 to show up. So something like that. I won't go too crazy here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'll just go like 5 in each direction. Bless you. All right. And then I would suggest putting in your asymptotes first. They kind of like the bones, okay? They kind of give you some like guidance and some borders and direction as far as like how to, graph things. All right. So vertical asymptote at x equals 1. Okay, and yes, I'm going to label it here, VA x equals 1. All right. It's necessary because I believe in the past on the benchmark that we have in this class, which yes, we do have a benchmark, it happens at the end of the class kind of thing. I believe on the benchmark, they typically want you to, and I feel okay saying this because it shows on the practice benchmark, which you'll see, so I don't mind asking. But in the past, this has shown up on the benchmark, and when it shows up on the benchmark, they want you to like label the vertical asymptotes and stuff like that. So that's why I'm putting the label in here, just for the practice of it. If you're kind of like on your own, your teacher may ask you to do something else in a different class or whatever, but we're doing it here for this reason. Okay, I'm also going to put the horizontal asymptote in, so at 3, so like so, and again, I'll just abbreviate HA, y equals 3, except I really butchered the A there, so it looks like a blob. We also have a 0 at 0. That's easy to graph right there. Oh, actually, I'm going to use a different color at this point now. Okay, so with where we are right now, you can kind of see we have this single point in our quadrant, like over here, right? These asymptotes kind of like divide our graph up into like different sections, right? Different quarters. We have this quarter right here, this quarter, this quarter, this quarter. And so we know we got to go through this point. So I'm just going to kind of like, we know our graph's going to approach that vertical asymptote. We also know our graph's going to have to approach the horizontal asymptote eventually. So I'm just going to sketch it out like that. Okay, just kind of use that to approach the numbers. Okay. Are we going to have any of our graph show up here? Will any of our graphs show up here above our curve that we already drawn here? Will we have any graph up here? Why not? Wouldn't be a function anymore, would it? It would fail the vertical line test, right? So we know we don't have to worry about anything here. So then it's a matter of figuring out: are we going to have more function here in this kind of section, or are we going to have more function here in this section? And this is where those additional points come in. Okay, so I'm going to pick the point. Let's see here, 1, 2. I'll check 2. So we'll do f of 2 just to see what value we get here. That's going to be 6 over 1, or just 6. So at 2, 1, 2, we get 6. So 1, 2, 3, 4, 5. Of course, I pick one that's like not on the graph, but that's okay. Okay, so I'll put the point right there, 2, 6. And then we can see, aha, we're in this section. So again, I'm just going to kind of, and again, I didn't leave myself very much space there. So I kind of went off the graph. My apologies there. But there you get the idea, okay, of the graph. So yes, Ramika. Sure. Okay, so we're going to do that in the same way, or a very similar way, I should say, to what we did with infinity, right? We've got 3 times infinity to the 1. We have 1 times infinity to the 1. And so ultimately those infinities are going to kind of like, essentially like dwarf that -1. It's going to not be, consequential. And so it's really just going to be in the infinities will be in the ratio of 3 over 1. So it's just going to go to 3 then. We'll kind of simplify out and just make 3. Okay. Likewise here, we're going to have -3 times infinity. We'll have negative infinity to the 1, right? And 3 times negative infinity to the 1, I guess I should say. So again, in the same sense, the negative infinities are going to both grow kind of at the same rate almost, but in the ratio of 3 to 1. Because it's negative divided by negative, though, it's going to become a positive number still, 3. So it stays positive 3. Does that clarify enough for you there? Yeah, okay. We'll see an example, I think, tomorrow, okay, about like a situation where we're going to have 2 different horizontal asymptotes and when that will be different. All right, any other questions on this, though? I've got one for you guys to try otherwise. All right, hey. Then this one is for you, okay? So, I would like you to graph f of x equal to x squared minus 3x minus 10 all over x squared plus 3x plus 2. Okay. Now, do we notice anything about this rational function here? It factors. Okay, and the degree is different too. That's right. But we're going to factor it here. So I'm going to help you guys start off by factoring it. Okay. So the numerator is going to factor to what? Yeah, x minus 5 and x plus 2. 2 and 5 in a sense. And then what about the denominator? X plus 2 and x plus 1. Okay, now your temptation here is going to be to cancel out the x plus 2's. But don't do it, right? Because we want to graph this function and we want to keep these domain restrictions here, okay? But there's going to be 2 different kinds of domain restrictions that are going to show up here, right? You're going to have a vertical asymptote and you're going to have a hole in this graph. All right, so go ahead and give this a try. See what you can come up with here. And then say what? At the same point. It'll be impossible, but at different points. You can have one or the other kind of thing. So yeah, no, thank you for the presentation. Very good question. So do what you can with this. A few minutes and then we'll go over it together. Have you come in the meantime too if you're stuck on something. You want to make sure you're on the right path first. Besides, there's like 32 games going on right now. Just all it. Oh, perfect.
Oklahoma's gonna win.
If you get your bracket 100% right, you get $1 billion. What's that? Do I like goldfish? Yeah, they're pretty good.
Mr. Wood, how many possible brackets are there?
Yeah, a lot.
Mr.
So let's see.
White
There's you have 64 teams, right?
yeah.
So you have 64 teams, and then you have to pick 32 to win.
This is where the world
Mr. White said that if you find every single game you square it, like if you add up the number of games and square the number, you'll have.
Yeah, I'm trying to think here. There is a way to do this. This
Did
is
you
mathematical.
do this much time?
Yeah, I did.
I think I should start at 6:32.
Wait, last year wasn't Patrick Thomas the only one that did he tire them?
I have a funny story about math class that's related to horizontal.
I
All right, let's let me think because I just want to think about
Mr. Goff said like he went like 200 in like the world. Like
Oh,
what is
yeah.
that?
Gotta get one. You gotta get them all right though. Even if you, so like the thing is like this is like that's not so even being 100 in the world that's good, but I mean like if you miss just one,
Exactly.
you're out.
Yeah.
But
So to find the vertical asymptote,
like for the $1 billion prize, you have to
You
get
have to
every
get
single
every
one
single
right.
to find the vertical asymptote,
No, no one's gotten like I don't think even close to it.
to divide -3 by 3. So use -1, right? The vertical asymptote.
Would be at correct -1. Yes, -1 would be the vertical asymptote.
And the horizontal, well, the horizontal asymptote.
That's when you want to use the limit as exponential infinity.
Okay. All right.
Don't forget to find your whole
Oh, that makes sense. That makes a lot of sense.
Yeah.
I know.
Wait. Okay. So if you win the $1 billion, you have to get even like if there's like a tiebreaker.
I mean, I'm assuming like within the game the tiebreaker occurs, right? I mean, it's like you just go until overtime, and then whoever gets. I don't even know how the overtime stuff works. Yeah, it's just because the probability is so low. So.
Oh wait, Mr. Wood, did you want?
Oh, no, thank you.
Are you sure?
Yeah, I'm sure.
That's all Mr. Thomas. You can extra credit.
Not like behind you, the classroom.
He's done that.
That and peanut butter cups, right?
Extra credit.
What's his deal
I
with
feel like
gold?
peanut butter cups too.
I don't know. It's that he wants to win.
Who likes goldfish?
I'm sorry.
Because I bought him like an entire like
There was a topic algebra.
I really like
It
pickle
was,
up 8%.
I forget what teacher it was, but she
Buys
had
his
us
truck
fill
load
out
of
brackets.
Who wants
Okay,
one?
sure.
One extra credit.
And
I
for
was
some
getting
reason, this was in the 7th grade, so that's the year that Duke won.
Okay.
And I was the only person to guess Duke, and so I wanted to go to class.
Get him Reese's.
And she said, you can either have your chocolate bar or extra credit, and I got extra credit, and that's the reason I got it.
Get out like you needed the extra credit. I probably would have chosen the chocolate bar. Not gonna lie. But you saw me also buy 3 or 4 boxes. So 5 yes, and 2 no would be a no because that also makes your denominator something too. So just 5.
Me, thank you.
Because you're taking one of this.
So like I was
Exponential
full No, I
Like 1 more minute here, 1 more minute. So 0.
Checking the homework. Your mic is
So that's a whole.
yeah, I'm like, oh.
Yes.
I'm so sorry for being so loud. Okay, so I was trying to like sketch, but I stopped the sketch. My brain didn't work, so I started laughing because I couldn't write more. It just said sketch. No, yeah. So I laughed at sketch. But then so now we have a band name. We have a band name called sketch. No syphilis.
Open up for.
Oh, not the syphilis. Yeah.
Define the zero.
Yeah, they were just 16
Yeah.
So zero function equals zero.
I got it.
Rational function equals zero. Fraction. Well, so right? You see why that is? So, but the thing is, -2 gives you more than just zero numerator. -2 also gives you just -2.
Well,
Indicates it's a whole relative. So you don't put it as a zero, it's a whole. But 5 gives you a number in the denominator, zero that makes it that's a whole.
Don't you plug the negative 2
well, you have to cancel out the
Good, I
negative
went to,
So like you plug it
My mom talks about it.
My family, we got the big fight.
Oh my god.
so thankfully I was a good one. Also, I didn't like my wife's family, they're like,
How did
a
that happen?
fight, but it got like,
Yeah, that's
it got like awkward, like her
Yeah.
sister just frustrated and started texting on her phone and stuff like that.
It's just your
Yeah, started getting goofy, and so like she
Yeah.
started getting like frustrated.
Mine's
So
like a Harvard
luckily, yeah, so luckily we were all like just friends, and I guess like we were all like kind of into it. You know?
Yeah.
So, like, it was cool. Yeah, so we made it out in like 50 seconds.
Oh, I didn't do 50 seconds. No, like that.
There was like 10 minutes left, and like we popped open like the fireplace, and there was another room, like, oh no, it's like this. And there were like all we were like spread apart in like a secret room kind of thing. And it's like there's one of the things, and like, you know, my wife was in the last lot, and like grabbed it and piece and brought it to someone, and like grabbed like the top. Now, I definitely you're smart about it.
I think we should all do it as a math class. That's like,
What's your
the reason why there's a whole is because x plus 2 is on the top of the line.
Okay, folks, let's take a look here. Okay. Domain restriction. Do we have any? Yes. At what 2 points are we restricting from the domain? -2, -1. So our domain then is going to look like this. -infinity to -2 union -2 to -1. Don't forget this interval between -2 and -1. Those points are okay, right? Union -1 to infinity. Okay, so there's our domain. Okay, so these domain restrictions, we don't want x to be -2, we don't want x to be -1. These are going to result in either horizontal asymptotes or vertical asymptotes. So keep these in mind for later, like the next step here, okay, where we identify any vertical asymptotes. Do we have any vertical asymptotes? When x is equal to what? X is equal to -1. Why not x equals -2? That's also a domain restriction. Right, what indicates it's a whole? When we get -2 plugged in here, -2 gives us 0 on the top and on the bottom, indeterminate form, indicating a whole. -1, if we plug it into the top, you get a number, okay, not 0, and then in the denominator you do get 0. So this gives us undefined, and so there's our vertical asymptote. So then the whole, right, we said occurs at x equals then -2, right, we said that, okay? But that's the x coordinate. A whole is like a point. It needs to have a y coordinate as well. So, Riley, plug it back into the equation, but we're going to plug it back into the factored and canceled form, okay? Because again, if If we just said plug it back into the original, right, well, that's going to give us 0 over 0 here. But now we can cancel these x plus 2's, plug in the negative 2 now. We'll evaluate it at x equals negative 2. And so we get then negative 7 over a negative 1, or just plain old 7 there. So the whole, okay, is at negative 2 comma 7. So we get a point, in a sense. It's like a non-point, but we can use it as a coordinate. Okay? So let me just pause right there. Any questions up through this? 1, 2, or 3? Okay. If you decide you do have a question, let me know. All right, number 4, the zeros. Where do we have any zeros? At x equals 5. Okay? A function equals 0 when its numerator is 0. So if we set this numerator equal to 0, well, wait a minute here. We have 5 as a 0, but isn't negative 2 a 0? Why not? Negative 2 is a whole, right? Okay, negative 2 is a whole. It's also restricted from the domain, right, because there's a hole there. Okay, so it can't be a 0. It's restricted. Okay, and then number 5, do we have any horizontal asymptotes? Yes, okay. And where are horizontal asymptotes? At x equals 1. Yeah, the limit as x approaches infinity of f of x. Use your degree rules here. The degree at the top is the same as the degree of the bottom, so it's the ratio of the lead coefficients. It's just 1. Okay. Will we always have a horizontal asymptote? Not necessarily, right? We have degree rules here where the limit might not exist. Okay, that would be no horizontal asymptote. And if the degree of the bottom is bigger, then we'll have a horizontal asymptote at 0 or on the x-axis there and stuff. So, okay, question, yeah.
Which one is when we have a slant asymptote? Because I know we know that.
When the degree on top is 1 greater than the degree of the bottom. Okay, degree of the numerator is 1 greater than the degree of the bottom, and then we get to do long division. Very exciting. But we won't do that till tomorrow, so you'll have to wait. I know. Okay, so whoop, I already drew x there. Don't need to draw it again. Okay, so let's see here. I need to go to 7 on the x-axis, it looks like. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, so let's see if I've got enough points here. So I have a 0 at x equals 5. So 1, 2, 3, 4, 5. I'm going to do this in red. Okay, there's my 0. Vertical asymptote at x equals negative 1. Okay, like so. Hole at negative 2, 7. 1, 2. 1, 2. Wow, I put 7 for the x-axis. It's supposed to be y-axis. Oh, well. 1, 2, 3, 4, 5, 6, 7, we'll say, is up here. Oops, except it's a hole. There we go. Open circle for the hole. Something like that. There we go. Okay. And we also have a horizontal asymptote I forgot to put at 1. Okay, I really don't think you need any more additional points here because we have a point here indicating this kind of quadrant here, so I'll just kind of do something like this. If you wanted to, you could find the actual y-intercept here. That's your choice. Don't need to, though. I didn't ask you to do that, so no worries. And then the rest of the graph will look something like this. Okay, don't draw through the hole, right? A hole is a hole, so we want to keep it open there like that. And there's our sketch. All right, questions on any of that? Too easy? Yeah, all right. I'll give you guys your, almost bit it. Oh, good, so good. We're alive. I put my foot in your pocket, or my own jacket pocket, I think, or something there, so, yeah, it's okay.